All right, welcome back. Today we're looking at section 10.5, which is all about permutations and combinations. Now, those words might not be familiar, but by the time we're done with this section, I think that you'll have a pretty good understanding. So let's get into it. So a permutation is an arrangement of objects where the arrangement has a very specific order. And what I mean by that is that the order is important. So if we look at the number of possible permutations for the letters A, B, and C, there are 6 different ways we could arrange those letters. And they are listed here for you. We could say A followed by B followed by C. We could say C followed by B followed by A. And what we're saying is that if we think of these as words, even though nobody thinks of ABC as a word, but if we think of these letters as words, those would be different words. Now, they have the same letters, but they are different because the order is different. So a permutation is an arrangement of objects in which the order is important. So let's take a look at example 1 and see if we can do a couple problems that make use of this idea. So example 1 says, consider the number of permutations of the letters in the word July. In how many ways can you arrange all of the letters? And how many different ways could you arrange 2 of the letters? Let's just focus on problem A. So when I think about arranging all of the letters in July, I think about 4 different positions that I could put a letter in. I have 4 letters to choose from. So in the very first position, I have 4 different objects that I have to choose. Once I've made a choice, though, I no longer have that as an option. I have 1 less to put in the second position, and 1 less than that to put in the third position, and 1 less to put in the fourth position. When you multiply these all up, what you end up getting is 4 times 3, 12 times 2, 24, 24 different permutations. And that's an important word to keep track of because we're going to often get that confused with combinations. But there are 24 different permutations using the letters J, U, L, and Y, or using all 4 letters in the word July. Now, problem letter B is approaching it from a different lens. It's saying we're still going to use the 4 letters, but we only want to make combos that have 2 elements in it. So we're really looking at a 2-positioned object, and we have 4 choices for the first spot and 3 choices for the second spot. So we actually have half as many. There are 12 different permutations, but 12 different permutations, 12 different 2-letter permutations using J, U, L, and Y. Okay. Now, this idea of multiplying 4 times 3 times 2 times 1 actually has its own special kind of mathy thing, and we'll get into that. But let's see if we can take a look at problem number 1 here and make sure we understand how to apply this. This would be a good time to pause, or you can go ahead and continue to follow along if you'd like. So in how many ways can you arrange the letters in the word house? Well, in problem number 1, there are 5 letters in the word house. How many different ways can we arrange that? Well, we have 5 letters to choose from in the first spot, 4 letters to choose from in the second, and so on. So 3 times 2 times 1, and so 5 times 4 being 20, times 3 being 60, times 2 being 120. There are 120 different permutations that you could create out of the letters in the word house. Problem number 2. It says, how many ways can you arrange 3 letters out of the word March? Now again, we have 5 letters in the word March, but we're only going to make use of 3 of them. So we're going to say 3 slots, 5 choices for the first, 4 for the second, 3 for the third. So 5 times 4 being 20, times 3 being 60. 60 different 3-letter permutations of the word March. Okay, now, like I said earlier, when we started a number and we multiply all the way down to 1, that does have a mathematical concept, and we call that a factorial. And so that word factorial might be new, but factorial basically lets us say that we're going to take a number and multiply by all of its previous integers until we get down to the number 1. So 4 factorial, we would say, is 4 times 3 times 2 times 1. Now, we do write it using an exclamation point, which oftentimes can be a little confusing, but understand that when you see a 4 followed by an exclamation point, we call that a 4 factorial. So here they're showing you n factorial, where we start off with the number n, we multiply by 1 less than that, so times n minus 1, times n minus 2, all the way down until we get times 2 times 1. So n factorial is defined here for you. And what I would suggest is that you have that definition in your brain, because we're going to use that when we start talking about a formula for permutations. Another key concept to keep in mind is that 0 factorial is defined as the number 1. If you're looking for a good proof for that, this is not the place to maybe discuss that, but if you're looking for a reason, it's the terrible parent reason of it is because I said so. So let's take a look at our permutation formula. The permutation formula for the number of objects taken within n group at a time is simply n factorial. So we have 4 objects taken 4 at a time, then it's just simply 4 factorial. But oftentimes we're looking at finding the number of objects taken at less than that. So notice how we're saying that r is going to be maybe less than or equal to n. So we have n objects taken at r at a time. It's a very different formula. And so this, I'm going to put a box around this. You're going to want to write this formula down. We are going to make use of that as we do problems today. That the number of permutations is found by taking n factorial divided by n minus r factorial. So let's see if we can make use of this in the problems to come. All right. So using a permutations formula, 10 horses are running in a race. How many different ways can the horses finish first, second, and third? And again, hopefully we recognize that finishing in a race, the order is important. If you get the gold medal, it feels very different than if you get the bronze medal. So the order is important, so we want to account for all of those differences amongst the order. So we have 10 horses, and we're looking for the number of permutations taken 3 at a time. So we're looking at 10 factorial over 10 minus 3 factorial. Now the reason why factorials are kind of nice to work with is it actually makes for some easy arithmetic. So I'm going to rewrite this again, 10 factorial over 7 factorial. Now some people will say easy arithmetic is not anywhere close to what this is. It's actually very tedious, but if we write this out, and we're not going to do this all the time, but if we write this out, 10 times 9 times 8 times 7, and then we say dot, 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 down to the number 1, the denominator is going to look like that as well, 7 times 6 times all the way down to 1. But lo and behold, we have all of those same values in the denominator in the numerator. So we can just cancel all of this out. And what we're left with is 10 times 9 times 8, which is 720 different ways that 10 horses could finish in first, second, and third. So it's quite a good number of ways that could happen. Now, let's consider a different problem here. So this is where we're using probability and permutations together. So keep in mind, Unit 10, we're using this idea of probability. Now we're going to incorporate the idea of permutations. So for a town parade, you will ride on a float with your soccer team. There are 12 floats in the parade, and their order is chosen at random. So find the probability that your float is first and that the float with the school chorus is second. So presumably, maybe we want to be first in the parade. Presumably, we want to have the chorus team follow right behind us. And we're wanting to know how many different ways could we expect for that to happen. Well, I can tell you, we first want to know how many different ways can we arrange all 12 floats in the parade. So we're looking at the total number of ways to arrange 12 floats taken 12 at a time. That's going to be our denominator. So 12 objects chosen 12 at a time is simply 12 factorial. Now, the other thing we need to keep in mind is that is the denominator of our probability. That's the bottom of our fraction. But what's the top look like? Well, there's only one way for the soccer team to be first, and there's only one way for the chorus team to be second. But what about all the ways for the teams that follow us to go in the parade? So there are 10 teams left over that could be arranged in a group of 10. So that's looking at it as 10 factorial. So our probability then is 10 factorial over 12 factorial. Now again, if we write all this out, we're looking at 10 multiplied down to 1. We're looking at 12 times 11 times 10 all the way down to 1. We are going to get some simplifying here. So we're looking at 1 over 12 times 11, which is really just 1 over 132. which is not a good chance that if we wanted to be first and we wanted chorus to go second, probably not a very likely chance that that would happen at random. We'd probably have to make sure we did something so that we were first and that chorus went second. All right, so let's take a look at a couple of what ifs. So this again would be a great time to pause if you want to work these problems on your own, but problem number 3 says in example 2, suppose that there are 8 horses in the race, and in how many different ways can they finish first, second, and third? So it looks like we're taking 8 objects, and we're wanting to know the number of permutations when we take them 3 at a time. So 8 factorial over 8 minus 3 factorial. Looks like 8 factorial over 5 factorial. And that looks like 8 times 7 times 6 times 5 all the way down to 1. Whereas the denominator looks like 5 all the way down to 1. So again, these will cancel, and we're looking at 8 times 7 times 6, which of course 8 times 7 times 6 is simply 336, kind of a big number. A lot of different ways for 8 horses to finish first, second, and third. Now, problem number 4, it says, considering example 3, suppose that there are 14 floats in the parade. Find the probability that soccer would go first and chorus would go second. So again, the total number of floats has been increased, so we're looking at 14, taking 14 at a time. What are the number of permutations there? Well, that's 14 factorial. We still are wondering how soccer can go first and chorus can go second. So that means there's 12 teams that follow us. How many different ways could those 12 teams go? Well, they could go 12 factorial. The probability then would be 12 factorial over 14 factorial. And so this will give us a chance to kind of play with the arithmetic again here. So 12 multiplied down to 1, 14 multiplied by all the way down to 1. So what we're really looking at is 1 over 14 times 13, which is the number 182. So again, it's not a very good chance that if we wanted to go first in the soccer team and the chorus to go second, that would happen if we were going to just choose that randomly out of all the different ways it could happen. All right, so a different word altogether. This idea of combinations is completely different. So what is a combination? A combination is a little different than a permutation. A combination is where we still are looking at the number of ways that things can happen. It's the number of ways we can order objects, but the order of that object is not important. And that's really, really critical to making sure we don't get these confused. So for instance, if we're not necessarily going to give a gold medal to the first place winner and a silver medal to the second place winner and the third place winner gets a bronze, we're just going to give them 3 prizes, then the order doesn't necessarily matter because they're all getting the same prize. So for the number of combinations, there typically is less when you're considering all things being equal. So let's take a look at how we would do this, and let's take a look at a problem where we're talking about letters. So count the possible combinations of 2 letters chosen from the list A, B, C, and D. Now it's interesting when we look at these types of problems, we have to start kind of thinking about, well, what would it look like if we were to write them all out? So here they are, they're all written out, but we first recognize that we have AB here, and we also have BA here. Well, technically those are the same. You know, if we're just talking about a two-person group, we would have the same 2 people, so we're going to get rid of this because it's a double. And so if I have AC here, then I have CA here, and that technically is a double, so I can get rid of it. If I have BC here, I can technically get rid of CB. So what are we looking at in terms of unique options? I'm going to just go ahead and circle all the unique options, whereas the rest of these, they all are technically already been counted for. So the total possible combinations of 2 letters chosen from letters A, B, C, and D would simply be 1, 2, 3, 4, 5, 6 different, and this is important to note, 6 different combinations where we're looking at 2-letter combinations considering A, B, C, and D. Now, let's take a look at a problem that sort of looks like this. Count the possible combinations of 3 letters chosen from A, B, C, D, and E. Now, if we're only looking at 3-letter combinations, let's keep in mind what we have here to choose from. We have 5 letters up here. So if we're thinking about 3-letter combos, let's go back to this idea. I have 5 letters to choose from for the first. I have 4 letters to choose from the second and 3 to choose from the third. That would be 60 different things to write out, and then consider we have a bunch of doubles or a bunch of repeats where the order is necessarily changed up, but the letters aren't different. So that's a lot to write out. So we're going to actually kind of help us to understand that writing all of these out is not the best way to go. What we need to realize is that the order isn't important because they're asking specifically for combinations, and there is a formula for this. So let's skip down to the formula here, and then we'll go back. So for the number of combinations taken n at a time, r at a time, is going to be n factorial divided by n minus r factorial times r factorial. And again, what is r? R is the number of objects that you're taking in a given group. So let's go back to the previous problem and see if we can make sense of this. So in the previous problem, we have 5 letters chosen 3 at a time. So we're looking at 5 objects chosen 3 at a time. So it's 5 factorial over 5 minus 3 factorial times 3 factorial, and that's in the denominator. So let's rewrite this again. 5 factorial over 5 minus 3 being 2 factorial times 3 factorial. Now what I need you to do is stop and pause here. 2 factorial times 3 factorial is not 6 factorial. Let's just write this out. So I've got 5 times 4 times 3 all the way down to 1. I've got 2 times 1 times 3 times 2 times 1. Well, the 3 factorial down to 1 will cancel with this one. And of course, the 4 on the top and the 2 on the bottom will also reduce. So we're looking at 20 divided by 2. There are 10 different 3-letter combinations when choosing from A, B, C, D, or E. So that is our formula that we're going to want to use. We're going to want to make sure that we have this formula written down. Put this thing into your notes. We'll be using this quite a bit when we're in this section. Okay, let's keep moving then. Let's take a look at another example where it says you're ordering a sandwich. So you have 2 side dishes from a list of 8. How many combinations of side dishes are possible? So again, the order in which I get my side dishes, if I get my French fries first or if I get my fruit cups first, the order is not important. I still have the same meal, but they want to know how many different meals could you have where you have 8 different sides to choose from and you get 2 of them. So 8 combinations taken 2 at a time is 8 factorial divided by 8 minus 2 factorial times 2 factorial. So we're looking at 8 factorial divided by 6 factorial times 2 factorial. So we're looking at 8 times 7 times 6 all the way down to 1 divided by 6 all the way down to 1 times 2 times 1. Now, as we talked about earlier, the 6's all the way down will cancel. 8 divided by 2 is 4, and so 4 times 7 is 28. There are 28 different combinations you could have where you get groups of 2 out of 8 to choose from. So one more time, maybe press pause if you're not wanting to see how to work this through, but let's see if we can do this problem here. So we have the same scenario above. We have 8 side dishes, and now you're choosing from 3, so it's just 8, choose 3, 8 factorial over 8 minus 3 factorial times 3 factorial, 8 factorial over 5 factorial, 8 times 7 times 6 times 5 all the way down to 1, divided by 5 times all the way down to 1 times 3 times 2 times 1. The 5's will cancel. 3 and 2 is 6, so the 6 will cancel with the 3 and the 2. We're saying 8 times 7 is, not 8, is 56 different combinations of 3 side dishes. Now, I hope that helped. I hope oops, I think I might have made a mistake there. Let's go back and double check. I think I made a little bit of a mistake. Oh no, that's good. 8 times 7 is 6, or 8 times 7 is 56, so we're good. I hope that helped. I hope that you can make some sense of that. And obviously, if you have questions, please ask them.